China is rewriting the rules of what's physically possible. It is currently building projects so massive, they make the Panama Canal look ancient. We're talking about moving entire rivers across a continent, drilling tunnels under seas that engineers said were impossible, building dams that generate more power than some countries consume in a year. Don't miss out as we count down the 9 biggest infrastructure megaprojects China has ever built. From railways that defy the laws of physics to water diversions that seem impossible, these are China's most impressive creations. Let's start at number 9. Imagine trying to build a railway to the roof of the world. That's exactly what's happening across the Tibetan plateau right now, where trains will soon be racing at 250 kilometers per hour through terrain where most people need oxygen tanks just to walk. And if you think that sounds difficult, you haven't heard the half of it. Tibet sits on a plateau averaging 4,500 meters above sea level. That's higher than most commercial aircraft fly when they're cruising. Construction workers can't swing a hammer for more than a few minutes without gasping for breath. Concrete takes twice as long to set, and diesel engines lose nearly half their power. And then there's the ground itself. Much of the route crosses permafrost, ground that's been frozen solid for thousands of years. You might think frozen ground would be stable, perfect for building on. Except when you put a railway on top of it, the ground starts to warm up. The permafrost melts. What was once solid earth turns into unstable mud that can swallow entire sections of track. Engineers watch test sections sink meters into the ground within months. The solution they came up with reads like science fiction. They're building the railway on thousands of elevated bridges, but these aren't ordinary bridges. Inside the support pillars, liquid ammonia circulates through a network of pipes, acting like a massive refrigeration system. The ammonia absorbs heat from the ground, keeping the permafrost frozen even as 200-ton trains thunder overhead at high speed. Each pillar is essentially a giant freezer, working 24/7 to fight against the natural warming effect of the railway itself. At these altitudes, diesel locomotives lose so much power they can barely pull their own weight, let alone a full passenger train. China developed specialized locomotives with turbocharged engines that force extra air into the combustion chambers, compensating for the thin atmosphere. Even with this technology, the trains need more powerful engines than equivalent railways at sea level. Then there's the human factor. Passengers traveling at these altitudes for hours would experience severe altitude sickness. Maintaining an artificial atmosphere equivalent to 2,800 meters, even when the train is traveling at 4,500 meters. Oxygen is pumped into the cars continuously. Medical staff ride on every train. Emergency oxygen masks are built into every seat. The construction logistics alone are staggering. When something breaks, and at this scale, something always breaks, the nearest city with adequate supplies might be 1,000 kilometers away. Workers couldn't just order materials and expect delivery in a few days. They had to build entire temporary cities on the plateau, complete with concrete factories, steel fabrication plants, power generation facilities, and housing for over 100,000 workers. These camps operate in temperature swings from 30 degrees Celsius during the day to -20 at night. The existing Qinghai-Tibet Railway, completed in 2006, was already considered an engineering marvel, but that line tops out at 160 kilometers per hour. The new extensions push speeds up to 250 kilometers per hour through even more challenging terrain. Routes to Nyingchi snake through valleys where the Indian and Eurasian tectonic plates are actively colliding, pushing the Himalayas upward by about 5 millimeters every year. The track beds are designed with flexible joints that can handle the ground shifting during earthquakes without derailing trains. Some sections required drilling tunnels through mountains at elevations where even the tunnel-boring machines had to be specially modified to operate. The air inside the tunnels during construction was so thin that diesel equipment wouldn't run properly. They had to use electric machinery powered by generators, creating a whole additional layer of complexity. Different segments are at different stages of completion. Some sections are already operational, cutting travel times dramatically. Other sections are still in active construction, blasting through mountains, spanning impossible gorges with bridges that seem to hang in midair. laying tracks across permafrost that constantly threatens to undermine the whole enterprise. Full completion of the entire network won't happen until the 2030s, and even that timeline assumes no major setbacks. When finished, this will be the highest railway network on Earth, operating in conditions that would shut down virtually any other transportation system. Travel times from Beijing to Lhasa will drop from over 40 hours to potentially under 15. Tourism, development, and economic integration will accelerate. But there's a cost beyond the engineering challenges. Critics point out that easier access accelerates cultural change in one of the world's most unique regions. Environmental groups worry about the impact on fragile, high-altitude ecosystems, and there's no ignoring the strategic angle. A high-speed railway to Tibet makes it much easier to move military resources to sensitive border regions. When it's done, it will be the highest railway on Earth, operating in conditions that would shut down virtually any other transportation system on the planet. It's engineering at the absolute edge of what's possible. But as impressive as building a railway to the sky sounds, we are only beginning. Because what comes next harnesses more raw power than almost anything humanity has ever built and literally changed how fast the Earth spins. When you concentrate 39 billion cubic meters of water at a higher elevation than it would naturally sit, you change Earth's moment of inertia. The planet's rotation slows down, not by much, just 0.06 microseconds per day, but enough for the scientists to measure it. That's the scale we're dealing with when we talk about the Three Gorges Dam. China needs such an extreme dam to deal with. The Yangtze River, the longest river in Asia, which regularly flooded with devastating consequences. For centuries, these floods killed thousands, destroyed crops, and wiped out entire communities. At the same time, China's explosive economic growth demanded massive amounts of electricity. Coal plants were choking cities with pollution. The country needed clean energy and flood control, and they needed it at a scale that matched their population of over 1 billion people. The solution was to build the world's largest hydroelectric dam right in the middle of the Yangtze, a dam that would create a reservoir 600 kilometers long, stretching back through some of China's most iconic landscapes. Construction began in 1994 on the Yangtze River, and from the first day, nothing about this project was ordinary. The dam wall stretches 2.3 kilometers across the river valley and rises 181 meters, roughly the height of a 60-story building. But calling it a building doesn't capture the sheer mass of the thing. They poured 28 million cubic meters of concrete, 16 times more than the Hoover Dam. At peak construction, 26,000 workers were on site around the clock, essentially building a small city out of concrete that had to be strong enough to hold back a reservoir containing 39 trillion kilograms of water. Think about what that means for the construction process. You can't just pour concrete in a solid mass. The chemical reaction that makes concrete harden generates enormous heat. In a structure this large, if you pour too quickly, the interior heats up while the exterior cools, creating temperature differentials that cause the concrete to crack and fail. Engineers had to pour in carefully planned layers, allowing each section to cool before adding the next. The concrete mix itself was specially formulated to generate less heat during curing. Even with these precautions, cooling pipes were embedded throughout the structure, circulating chilled water to control temperatures during the years-long curing process. But the dam is only part of the story. The Yangtze is China's main inland waterway, carrying cargo vessels that keep the country's interior economy running. Block the river with a dam, and you've just created an economic catastrophe. So they built the world's largest ship locks, 2 parallel systems of chambers that lift vessels 113 meters, the equivalent of a 30-story building. Each lock chamber is 280 meters long and 35 meters wide. Ships enter the lower chamber, massive gates close behind them, and millions of gallons of water flow in, lifting the vessel to the next level. It takes about 4 hours for a ship to transit from the lower Yangtze to the reservoir behind the dam. The power generation is what really sets this apart. 32 turbines, each one generating 700 megawatts, are housed in the dam. Combined output, 22,500 megawatts, roughly equivalent to 15 large nuclear power plants. In a good year, The dam generates over 100 billion kilowatt hours of electricity. That's enough to power multiple provinces. That clean hydroelectric power replaces coal plants that would have pumped millions of tons of CO2 into the atmosphere annually. But you can't build something this massive without consequences that ripple outward in every direction. Over 1.3 million people were relocated to make way for the reservoir. Entire cities, some with histories stretching back thousands of years, were submerged. Ancient temples disappeared underwater. Communities that had existed in the same location for generations were forced to move to new, often hastily constructed resettlement towns. The government called it necessary progress and paid compensation. For many who lost their homes and ancestral lands, no amount of money made it right. The environmental impact continues to generate debate. The reservoir traps sediment that the Yangtze would naturally carry downstream. That sediment used to nourish farmland and ecosystems along the river and in the delta. Without it, erosion patterns have changed. Farmland productivity has declined in some areas, and the coastline is actually retreating in places. Fish populations crashed when their migration routes were blocked. The Chinese river dolphin, already endangered, may have been pushed to extinction, partly because the dam fragmented its habitat beyond recovery. Landslides around the reservoir have become more frequent. As water levels fluctuate seasonally, the ground along steep valley walls becomes saturated and then dries out, destabilizing slopes that were stable for millennia. Some landslides have been large enough to create tsunami-like waves in the reservoir, threatening communities along the shore. Yet the dam has also prevented catastrophic flooding. In 2010 and 2012, floods that would have killed thousands and caused tens of billions in damage downstream were controlled by the reservoir's storage capacity. The dam's operators can hold back water during peak floods and release it gradually, protecting cities that would otherwise be inundated. This flood control benefit alone, supporters argue, justifies the project. The dam opened for power generation in 2003, with the final turbines coming online in 2012. The official cost was approximately $37 billion. But that doesn't account for relocation expenses, environmental mitigation efforts, or the lost cultural heritage now buried underwater. The true cost, economic and otherwise, is still being calculated decades later. Today, the Three Gorges Dam stands as both triumph and tragedy, a monument to human capability that produces clean energy for hundreds of millions of people, while serving as a reminder that megaprojects of this scale always extract a price. Next, we have yet another dam, which might not be as big, but the difficulty of construction makes it equally impressive. Completed in 2022, Baihetan is the world's second-largest hydroelectric dam by capacity. It sits in a gorge so deep and narrow that standing at the bottom feels like being at the base of a vertical cliff that stretches up into the clouds. The Jinsha River has carved through solid rock here for millions of years, creating a canyon over 500 meters deep. This is where China built what might be the most technically sophisticated dam in the world. The dam rises 289 meters from its foundation, significantly taller than Three Gorges, and uses a double curvature arch design that makes it look like a massive concrete bow stretched across the canyon. This isn't just aesthetic. The arch transfers the enormous pressure of the reservoir into the canyon walls, rather than relying on the dam's mass to resist the water. It's an elegant solution to building in a confined space, but it requires the rock on both sides of the canyon to be absolutely solid. Any weakness in the canyon walls and the entire structure could fail catastrophically. What really sets Baihetan apart is the turbines. Each of the 16 turbines generates 1,000 megawatts, 1 gigawatt per turbine. These are the largest, most powerful hydroelectric turbines ever built. For comparison, the Three Gorges turbines max out at 700 megawatts each. Each Baihetan turbine could supply electricity to a city of several million people. The runner, the spinning part that the water pushes to generate power, weighs over 350 tons and has to spin at exactly the right speed while handling massive volumes of water flowing past at incredible velocity. The precision required is staggering. Any imbalance and the turbine would tear itself apart. Building something this powerful in a gorge this confined created engineering challenges that pushed the limits of what's possible with concrete. When concrete cures, it generates heat, a lot of heat when you're working with millions of cubic meters of it. This heat causes the concrete to expand, and then it contracts as it cools, creating cracks that can compromise the structure. In a dam where the concrete is under enormous stress from the water pressure, even small cracks can propagate into catastrophic failures. At Baihetan, engineers had to keep temperature differentials under control across 8 million cubic meters of concrete. They developed a new type of low-heat concrete that generates less warmth during curing, but even that wasn't enough. They embedded over 2,800 kilometers of cooling pipes throughout the dam, enough pipe to stretch from Beijing to Bangkok. Chilled water circulates through this network continuously, controlling temperatures during the years-long construction and curing process. It's like building air conditioning into the structure itself, except the room being cooled weighs tens of millions of tons. The location adds another layer of complexity. This gorge sits in one of the most seismically active regions in China. The 2008 Wenchuan earthquake, which killed nearly 70,000 people, originated not far from here. The dam had to be designed to withstand a magnitude 8 earthquake, ground shaking that would collapse most buildings, and still function. The arch design actually helps here because it can flex slightly during earthquakes, absorbing seismic energy rather than fracturing. But that meant anchoring the dam deep into bedrock on both sides of the canyon, drilling hundreds of meters down and injecting concrete to create a foundation that's effectively part of the mountain itself. Getting materials and equipment to the construction site was a logistical nightmare. The gorge is in mountainous terrain with few roads. Turbines weighing hundreds of tons had to be transported on specially reinforced trucks through narrow mountain highways with hairpin turns. In some cases, temporary access roads had to be carved into cliffsides just to reach the construction site. At peak construction, over 20,000 workers lived in camps built in whatever flat ground could be found or created near the gorge. Baihetan began generating power in 2021, with full operations starting in 2022. The dam produces about 62 billion kilowatt-hours annually, enough electricity to power a country the size of Norway. That power is transmitted eastward to coastal provinces via ultra-high voltage transmission lines that lose minimal energy even over distances of thousands of kilometers. The environmental and geopolitical implications mirror those of other Chinese megadams. On one hand, 62 billion kilowatt-hours of clean hydropower replaces coal generation that would produce 50 million tons of CO2 annually. On the other, the reservoir submerged ecosystems, displaced tens of thousands of people, and disrupted fish migration routes. The Jinsha River becomes the Mekong as it flows into Southeast Asia, so dams here give China significant control over water resources that affect downstream countries. From a pure engineering standpoint, though, Baihetan represents China pushing the boundaries of what's possible with dam construction. They took lessons from Three Gorges, applied them in far more challenging terrain, and produced a structure that's more technically sophisticated in nearly every way. And Baihetan is just one dam in a whole cascade China is building along the Jinsha River. Which brings us to number 6, where things get even more extreme as we enter the world of China's insane hydropower stations. While Baihetan grabbed headlines for its massive power output, there's another dam on the Dadu River that might be even more impressive from a pure engineering standpoint. It's taller, it's built in more difficult terrain, and it's using construction techniques that didn't exist a decade ago. When engineers talk about building tall dams, they usually mean concrete structures anchored into bedrock. The Shuangjiangkou Dam takes a completely different approach. At 314 meters tall, it is one of the tallest rock-filled dams ever constructed. But height is just half the story. The Dadu River carves through the eastern edge of the Tibetan plateau in an area where mountains rise abruptly from narrow valleys, and earthquakes are simply part of life. The rock formations are fractured from millions of years of tectonic stress. Winter temperatures regularly drop below -20 degrees Celsius, making construction possible only during brief windows of decent weather. The nearest major city is hundreds of kilometers away over mountain roads that sometimes wash out completely during heavy rains. Conventional concrete dams in this terrain would be monumentally expensive and potentially unstable. Concrete requires massive amounts of water for mixing and curing. Cement has to be transported in, and the whole structure relies on having solid, unfractured bedrock to anchor into. Here, the bedrock is compromised in places, and getting materials to the site would multiply costs exponentially. Rock-filled dams solve these problems by using what's already there: rock. The concept is ancient, but executing it at this scale requires precision that would have been impossible a generation ago. You're essentially building an artificial mountain, but one that has to hold back billions of cubic meters of water without leaking, shifting, or collapsing. The Shuangjiangkou Dam contains 27 million cubic meters of material. Every single cubic meter had to be sourced from quarries, crushed to exact specifications, transported to the dam site, spread in layers no more than a meter thick, and then compacted using massive rollers until the density met strict requirements. Too much moisture in the fill and it won't compact properly. It'll settle over time and potentially fail. Too little moisture and the particles won't bind together adequately. The construction team had to monitor and adjust continuously based on weather conditions, rock characteristics, and the behavior of previously laid layers. The dam isn't just one uniform mass of rock. It's built in carefully designed zones, each serving a specific purpose. At the core is a watertight barrier made of clay and silt, extracted from specific deposits and processed to achieve the right consistency. This core has to be absolutely impermeable. Any leakage path through it could lead to internal erosion that undermines the entire structure. Surrounding the core are transition zones of progressively coarser material, each zone engineered to filter any water that might seep through, preventing it from carrying fine particles that would create voids. The outer faces are armored with massive boulders that protect against erosion from the reservoir and weathering from the elements. Building this in layers while maintaining stability creates a delicate balance. As you add height, the weight compresses the lower layers. That compression has to be uniform, or the dam will develop differential settlement, some parts settling more than others, which creates stress concentrations that can cause failure. Engineers monitored the dam constantly during construction using thousands of sensors embedded throughout the structure, measuring settlement, pore water pressure, and stress levels in real time. Seismic design was absolutely critical. This region experiences frequent earthquakes, and the dam had to survive a magnitude 8.0 event, ground shaking powerful enough to level most buildings. Rockfill dams have an advantage here because unlike rigid concrete, rockfill can flex and absorb seismic energy without fracturing. But that only works if the design is right. Computer models ran thousands of simulated earthquakes, analyzing how different shaking patterns would affect the dam. The foundation was excavated deep into bedrock and shaped to optimize load transfer. Special drainage systems were installed to prevent water pressure from building up inside the dam during or after an earthquake. Construction began in 2014, and the challenges went beyond just engineering. The remote location meant building roads first, then establishing construction camps that could house over 10,000 workers in terrain that's inhospitable much of the year. They built concrete batch plants, equipment maintenance facilities, and power distribution systems, essentially creating a temporary industrial city in the mountains. Materials and equipment that couldn't be sourced locally had to be trucked in over mountain highways where a single breakdown could delay construction for days. The dam started impounding water in 2021, but full operations won't be achieved until 2025 as the reservoir gradually fills and the downstream cascade of dams comes fully online. At 314 meters tall, it creates a reservoir holding 2.7 billion cubic meters of water. The power output is 2,000 megawatts, which sounds modest compared to giants like Baihetan, but that misses the point of what Shuangjiangkou actually does. This dam sits at the top of a cascade system. Multiple dams stretch along the Dadu River below it, and Shuangjiangkou regulates the entire system. When downstream dams need more water to meet electricity demand, Shuangjiangkou releases it. During periods of heavy rain or snowmelt when too much water would overwhelm downstream facilities, Shuangjiangkou holds it back. It's flood control, power optimization, and water resource management all in one. Think of it as the conductor, making sure all the instruments in the orchestra play at the right time and volume. The strategic location matters too. The Dadu River Basin sits near Tibet and connects to the upper reaches of other major river systems. Control over water resources here translates to influence over water availability across a vast region, not just for hydropower, but for agriculture, drinking water, and industrial development. As climate patterns shift and water becomes more contested, projects like Shuangjiangkou become increasingly valuable beyond their immediate function. Environmental concerns about the cumulative impact of so many dams on one river system are legitimate. Fish populations have declined dramatically. The natural sediment flow that shaped the river and nourished downstream ecosystems for millennia is now interrupted. The river's flow regime is regulated by dam operators rather than natural seasonal variations, fundamentally changing how aquatic ecosystems function. China's calculation is straightforward. They need the power, they need the flood control, and they have the technology to build these structures safely in challenging environments. Shuangjiangkou demonstrates that capability. It's a rock-filled dam that rivals the height of concrete dams while operating in seismically active, high-altitude terrain. Still, as technically impressive as Shuangjiangkou is, it's about to be dwarfed both in scale and controversy by what's coming at number 5. Because the next project isn't just big. It's being built in one of the most remote, geologically unstable, and politically sensitive regions in the world. There are places on Earth where building anything is almost suicidal. Medog County, deep in Tibet on the edge of the Himalayas, is one of those places. It's where the Yarlung-Tsangpo River makes a dramatic bend, the Great Bend dropping through one of the deepest gorges on the planet. And China is building what could become the world's largest hydropower station right there. Let's talk about why this is insane. The Yarlung-Tsangpo River flows relatively peacefully across the Tibetan plateau until it reaches the eastern Himalayas. Then it encounters a wall of mountains and is forced to turn nearly 180 degrees, carving a gorge that plunges over 5,000 meters from rim to bottom, almost twice as deep as the Grand Canyon. In a short stretch, the river drops 2,000 meters in elevation, creating some of the world's most powerful rapids and waterfalls. That elevation drop represents enormous hydroelectric potential. Gravity is pulling that water down with tremendous force. Capture that energy, and you could generate power on a scale that makes even 3 gorges look modest. The estimated capacity? Around 60,000 megawatts. That's nearly 3 times the output of 3 gorges. It would be the most powerful hydropower station on Earth by a massive margin. But building it requires solving problems that seem almost impossible. First, there's the geography. Medog County was the last county in China to be connected by road, and that road is only open part of the year due to landslides and snow. The terrain is so steep and unstable that simply accessing the construction site requires tunneling through mountains for kilometers. The bedrock is fractured from tectonic activity. Landslides are common. The area receives some of the heaviest rainfall in China, which triggers constant erosion. Then there's the seismic risk. This region is where the Indian tectonic plate is colliding with Eurasia, pushing up the Himalayas at about 5 millimeters per year. Major earthquakes are not a question of if, but when. The 1950 Assam earthquake, which struck nearby, was magnitude 8.6 and caused entire mountainsides to collapse. Building a massive dam in this environment means designing for worst-case scenarios that would destroy conventional structures. The engineering solution involves building not one giant dam, but a series of smaller dams and underground powerhouses connected by tunnels carved through the mountains. Instead of fighting the terrain, the design works with it. Water would be diverted through massive tunnels, dropping through turbines housed in caverns carved into solid rock, then continuing downriver to the next station. These aren't small tunnels. We're talking about water tunnels over 10 meters in diameter, stretching for tens of kilometers through tectonically active mountains. Each tunnel has to be lined with concrete and steel, reinforced to withstand earthquakes and the immense pressure of water flowing at high velocity. The powerhouses themselves would be underground massive caverns excavated from bedrock, housing turbines that each generate thousands of megawatts. Building these caverns requires removing millions of cubic meters of rock, all while ensuring the caverns remain stable in rock that's under enormous tectonic stress. Construction timelines are ambitious. Official reports suggest the project could begin major construction in the mid-2000s, with completion by the 2030s. But those timelines are speculative. The preparatory work alone, building access roads, conducting geological surveys, excavating exploratory tunnels, takes years in this terrain. And then there's the politics. The Yarlung Changpo becomes the Brahmaputra River as it flows into India and Bangladesh. A dam of this scale would give China enormous control over water flowing to two countries that together have over 1.5 billion people. India has already expressed concerns. Environmental groups point out that the ecological impact on the Brahmaputra basin could be catastrophic. China's position is that the dam is for power generation, not water control, and that it won't significantly affect downstream flow. But that's a hard sell when you're talking about the world's largest hydropower project on an internationally shared river. Domestically, the project is controversial too. Medog is home to unique ecosystems found nowhere else on Earth. The gorge's depth creates multiple climate zones, from subtropical rainforest at the bottom to alpine conditions at the top. Species that evolved in isolation could be threatened by construction and the altered river regime. There's also the question of cost. Estimates range from $80 billion to over $100 billion, making it potentially the most expensive infrastructure project ever attempted. For perspective, that's more than the entire GDP of many countries. Critics question whether it's even necessary. China already has massive hydropower capacity. Solar and wind are becoming cheaper. Why risk a project of this complexity and controversy? Supporters argue that hydropower is dispatchable. It can generate electricity on demand, unlike solar and wind. As China transitions away from coal, it needs reliable baseload power. A 60,000 megawatt hydropower station could stabilize the entire national grid. The Medog hydropower station is still in early stages, and it's possible the project could be scaled back or even canceled if challenges prove insurmountable. But if China commits fully, it will be one of the most ambitious engineering projects ever attempted. Yet, even this isn't the biggest water project on our list. Because while Medog is about generating power, the projects coming up are about moving water itself on a scale that's hard to fathom. But first, we need to go underwater. Imagine drilling a tunnel under the ocean, connecting two cities separated by one of China's busiest shipping lanes. Now imagine that tunnel is 123 kilometers long, longer than the Channel Tunnel connecting England and France, and runs under waters that are, in places, over 100 meters deep. That's the Yantai Dalian undersea tunnel, and it's not just an idea anymore. Planning is advanced, and if completed, it will be the longest undersea tunnel in the world. Here's why it matters. The Bohai Sea sits between northern China's Liaodong Peninsula and the Shandong Peninsula. It's a relatively shallow body of water, but its wide crossing from Dalian in the north to Yantai in the south requires either a long drive around the coast or a ferry ride that takes several hours. That geography creates a bottleneck. Road freight traveling from China's northeast to the rest of the country has to go the long way around. The ferry system helps, but it's limited by weather, can't operate in rough seas, and has finite capacity. For an economy that moves as much freight as China's, that bottleneck costs time and money. The solution? Tunnel under the Bohai Sea. The tunnel would run about 123 kilometers from shore to shore, making it roughly 50% longer than the Channel Tunnel. But unlike the Channel Tunnel, which runs through stable chalk bedrock, the Bohai Tunnel would pass through sediment, sand, and soft rock in a seismically active region that's also prone to strong ocean currents and winter ice. Engineering this tunnel requires solving problems that would make most engineers walk away. First, there's the length. Boring a tunnel 123 kilometers long is a logistical nightmare. Tunnel boring machines, TBMs, are enormous, the size of apartment buildings, and they can only bore in one direction. For a tunnel this long, you'd need multiple TBMs, starting from different points and meeting in the middle with millimeter precision. Any misalignment and the tunnels don't connect. The depth is another issue. In the deepest sections, the tunnel would run about 100 meters below the seabed, which itself is under 100 meters of water. That means the tunnel is under immense hydrostatic pressure. Water wants to get in. The rock and sediment want to collapse. Keeping the tunnel stable requires constant reinforcement with concrete linings, steel ribs, and sophisticated drainage systems to manage groundwater. Then there's ventilation. A 123-kilometer tunnel carrying vehicle traffic would generate massive amounts of exhaust fumes. Those fumes have to be removed and fresh air pumped in, requiring ventilation shafts and enormous fans capable of moving air through a confined space over 100 kilometers long. The tunnel would likely be built with two main tubes, one for each direction of traffic, plus a service tunnel in the middle for maintenance and emergency access. That's essentially building three separate tunnels simultaneously. Escape and safety are critical concerns. If there's a fire or accident in the tunnel, people need a way out, but you can't just open a door and leave. You're 100 meters underground beneath the ocean. The design would need emergency exits every few kilometers, connecting to the service tunnel with pressurized safe zones where people can wait for rescue. Earthquakes are a real risk. The Bohai region isn't as seismically active as some parts of China, but significant earthquakes do occur. The tunnel has to be flexible enough to handle ground movement without cracking or collapsing. That means joints, expansion gaps, and materials that can absorb seismic energy. The economic case for the tunnel is compelling. Current travel time between Dalian and Yantai is around 8 hours by land or ferry. The tunnel would cut that to under 2 hours. Freight costs would drop dramatically. The entire region would become more economically integrated. Cost estimates vary wildly, from $36 billion to over $50 billion, depending on the final design and construction method. That's enormous. But China has been willing to spend comparable amounts on other infrastructure projects. Construction timelines are still uncertain. Official planning has been ongoing for years, with various feasibility studies and route options analyzed. Some reports suggest construction could begin in the mid-2000s, with completion in the 2030s. But a project of this complexity could easily face delays. Critics question whether the tunnel is necessary. High-speed rail already connects the region, albeit indirectly. The ferry system works, even if it's slow. Is a $50 billion tunnel really the best use of resources? Supporters point to the long-term economic benefits. Infrastructure doesn't just serve today's needs, it enables tomorrow's growth. A tunnel that cuts travel times and freight costs could pay for itself over decades by enabling economic activity that wouldn't otherwise happen. There's also the prestige factor. Completing the world's longest undersea tunnel would be a statement of China's engineering prowess, joining projects like Hong Kong-Zhuhai-Macau Bridge as symbols of what the country can achieve. The Yantai-Dalian undersea tunnel is still in planning stages, and it's possible the project could be modified or even shelved if challenges prove too great. But if it moves forward, it will push tunneling technology to new limits. Of course, drilling under the Bohai Sea is impressive, but it's nothing compared to drilling through mountains to move water across an entire province. That's where number 3 comes in. China is running out of water where it needs it most. The country's north and west are dry, the south and east have plenty. The solution? Drill tunnels through mountain ranges and move the water. The Yunnan water tunnel is one of the most ambitious pieces of this strategy, and it's a project that sounds more like science fiction than civil engineering. Here's the problem. Yunnan province in southwest China has abundant water resources from rivers flowing off the Tibetan plateau. But much of that water flows south into Myanmar, Laos, and Vietnam. Meanwhile, central Yunnan, where the provincial capital Kunming is located, suffers from chronic water shortages. The region has over 30 million people and extensive agriculture, but rainfall is seasonal and unreliable. China's solution is to divert water from the Jinsha River, the same river that flows through the Baihetan Dam, eastward into the dry central regions of Yunnan. But there's a massive obstacle: mountains. The river is on one side of a major mountain range, and the areas that need water are on the other side, so they're drilling straight through. The Yunnan Tunnel is part of this system, and it's mind-boggling in scale. The tunnel is 38.5 kilometers long and over 9 meters in diameter, large enough to drive a 2-story bus through. It's one of the longest water tunnels in the world, carved through solid rock at depths of up to 700 meters below the surface. Drilling a tunnel this size through a mountain isn't like digging a hole in your backyard. The rock is under enormous pressure from the weight of the mountain above it. When you drill through, that pressure is released and the rock wants to collapse inward. Engineers have to constantly reinforce the tunnel with steel supports and concrete linings as they go. The geology makes it even harder. The rock isn't uniform. It varies from hard granite to fractured zones filled with groundwater. Hit a water-bearing fracture and suddenly you have thousands of gallons per minute flooding into your tunnel. You have to pump it out while continuing to drill forward. Then there's the methane. Some of the rock formations contain pockets of methane gas under pressure. Break into one of those pockets and you risk explosions or poisoning the workers. Every meter of advance requires careful surveying to detect gas pockets before you hit them. The tunnel has to maintain a precise gradient, a gentle slope, to allow water to flow by gravity from the higher elevation of the Jinsha River to the lower elevation of central Yunnan. Get the gradient wrong, and water either flows too slowly or too fast, causing erosion or sediment buildup. Ventilation is a life or death issue. Workers are drilling kilometers underground with limited air circulation. The tunnel needs extensive ventilation shafts drilled down from the surface, with fans pushing fresh air in and pulling stale air out. But drilling ventilation shafts through hundreds of meters of rock is its own engineering challenge. Construction began in the mid-2000s and is expected to continue through the mid-2000s. At peak construction, tunnel boring machines, TBMs, worked from multiple access points simultaneously, boring toward each other with millimeter precision. When the different sections meet, they have to align perfectly, or the tunnel won't function properly. The payoff is enormous. When complete, the tunnel will help divert billions of cubic meters of water annually from the Jinsha River to central Yunnan. That water will supply drinking water to cities, irrigate farmland, and support industrial development in a region that's been chronically water-stressed. But it's not without controversy. Downstream communities that depend on the Jinsha River worry about reduced water flow. Environmental groups point out that diverting water changes ecosystem species adapted to certain river flows now have to adapt to less water. And there's the international dimension. The Jinsha River eventually becomes the Mekong, which flows through Southeast Asia. Any water diverted in China is water that doesn't reach countries downstream. China's response is that the diversion is a small percentage of the river's total flow and won't significantly impact downstream users. But when you're moving billions of cubic meters, even a small percentage is a lot of water. The Shuangjiangkou Tunnel is part of the larger Central Yunnan Water Diversion Project, which includes multiple tunnels, pipelines, and pumping stations. It's a massive, interconnected system designed to move water from where it's plentiful to where it's needed. And speaking of moving water on a massive scale, that brings us to number 2 on our list, a project that dwarfs even this ambitious tunnel. If you thought one giant tunnel through a mountain was impressive, try imagining an entire network of tunnels, pipelines, reservoirs, and pumping stations designed to move water across an area the size of Germany. That's the Central Yunnan Water Diversion Project, and it's already under construction. The basic problem is simple but severe. Yunnan province has water in the wrong places. The western and southern parts of the province have abundant rainfall and river flow. The central and eastern parts, where most of the population and agriculture are concentrated, are dry. Kunming, the provincial capital with a metro population of over 6 million people, faces chronic water shortages. Historically, people adapted by using water sparingly and relying on limited local sources. But as the population grew and the economy developed, that strategy stopped working. Droughts became crises. Lakes and reservoirs dried up, agriculture suffered. Something had to change. The solution is to move water lots of it from the Jinsha River in the west to the dry central regions. The scale is staggering. The project aims to divert 3.4 billion cubic meters of water annually. That's enough to fill over 1.3 million Olympic swimming pools every year. But this isn't just about drilling one tunnel. The Central Yunnan Water Diversion Project is a complex, multi-phase system that includes over 660 kilometers of tunnels, including the Yunnan tunnel we just discussed, hundreds of kilometers of pipelines and aqueducts, multiple pumping stations to lift water over mountain ridges, reservoirs to store water for dry seasons, treatment plants to ensure water quality, distribution networks to deliver water to cities and farms. The route crosses some of the most geologically complex terrain in China. The region sits on the edge of the Tibetan plateau, with mountain ranges, deep valleys, and active fault lines. Tunneling through this landscape requires dealing with fractured rock, underground rivers, methane pockets, and high-pressure groundwater. In some sections, the tunnel is over 700 meters below the surface. That's deeper than 2 Empire State Buildings stacked on top of each other. At those depths, rock temperatures can exceed 30 degrees Celsius, making working conditions brutal for construction crews. The project also includes massive pumping stations that lift water hundreds of meters upward. Water is heavy. 1 cubic meter weighs 1 metric ton. Pumping billions of cubic meters of water uphill requires enormous amounts of energy. The project's pumping stations are some of the largest in the world, each with multiple high-capacity pumps powered by dedicated electrical substations. Water quality is another major concern. The Jinsha River water has to be treated before it's distributed to cities. The project includes multiple treatment plants that filter sediment, remove pollutants, and ensure the water meets drinking water standards. Construction began in 2016 and is being carried out in phases. Phase 1 focused on tunnels and basic infrastructure. Phase 2, currently underway, is expanding distribution networks and building additional storage capacity. Full completion isn't expected until sometime in the late 2020s. The cost is massive. Estimates range from $6 billion to $10 billion, depending on how you account for various components. That might sound like a lot, but consider the alternative. Without this project, Central Yunnan faces ongoing water crises that limit economic development and threaten quality of life for tens of millions of people. The benefits are already becoming apparent in areas where the project is operational. Cities that once rationed water during dry seasons now have reliable supplies. Farmland that was borderline viable is becoming productive. New industries that require significant water inputs are locating in the region. But critics raise important concerns. Diverting water from the Jinsha River affects ecosystems downstream. Fish populations change. Riparian habitats dry up. And there's the international aspect. The Jinsha becomes the Mekong, which flows through 6 countries. Water diverted in China is water that doesn't reach Myanmar, Laos, Thailand, Cambodia, and Vietnam. China maintains that the diversion represents a small fraction of the river's flow and includes agreements to maintain minimum downstream flows. But trust is in short supply when it comes to shared water resources. Domestically, there's concern about what happens if climate change alters rainfall patterns. The project assumes historical water availability in the Jinsha River. If droughts become more common, the amount of water available for diversion could decrease, making the entire investment less valuable. There are also questions about water rights and pricing. Who pays for this water? Should agricultural users pay the same as cities? What happens when demand exceeds the system's capacity to supply water? These are complex policy questions with no easy answers, but the physical project is moving forward regardless. Tunnels are being drilled, pipelines are being laid, pumping stations are coming online. The Central Yunnan Water Diversion Project represents China's confidence that engineering can solve resource scarcity problems. Whether that confidence is justified depends on factors, environmental, economic, and political, that will play out over the coming decades. But even this massive project, moving billions of cubic meters of water across an entire province, is only number 2 on our list. Because the number 1 megaproject is something that defies belief. A project so large that it makes Central Yunnan look like a local irrigation ditch. What if you could take the water from your country's wet southern regions and move it thousands of kilometers north to the dry regions where hundreds of millions of people live? It sounds impossible. It sounds insane. China is doing it. The South-North Water Diversion Project is the largest water diversion project ever attempted in human history. Not just in China, in the world. Ever. Here's the problem China faced. The North has most of the people, most of the agriculture, and most of the industry, but it has very little water. The South has abundant water, but far fewer people. The Yellow River, which flows through the North, is overexploited and sometimes runs dry before reaching the sea. Beijing, a city of 21 million people, sits in a region with less water per capita than Saudi Arabia. For decades, China managed this imbalance through a combination of groundwater pumping, strict rationing, and limiting development. But groundwater levels were dropping. Rationing was hampering economic growth, and the population kept growing. Something had to give. The solution, first proposed by Mao Zedong in the 1950s and finally implemented in the early 2000s, was to move water from the Yangtze River Basin in the south to the Yellow River Basin and northern cities. Not a little water massive amounts. The goal is to eventually transfer 44.8 billion cubic meters of water per year. To put that in perspective, that's enough water to supply the entire United Kingdom for nearly 2 years. Every year. The project consists of 3 massive routes: eastern, central, and western, each taking water from different points along the Yangtze and moving it north through different pathways. The eastern route starts near the Yangtze Delta and pumps water north through a series of canals, rivers, and lakes. It's over 1,150 kilometers long and includes multiple massive pumping stations because the route goes uphill. Water has to be lifted over 65 meters in elevation. Think of it as a staircase for water, where each step is a pumping station lifting millions of tons of water to the next level. This route became operational in 2013 and supplies water to cities in Jiangsu and Shandong provinces, eventually reaching as far north as Tianjin. The central route is even more ambitious. It starts at the Danjiangkou Reservoir on the Han River, a Yangtze tributary, and flows north via a specially constructed canal system. The route is 1,432 kilometers long, roughly the distance from New York to Miami, and supplies water to Henan, Hebei, Beijing, and Tianjin. The beautiful thing about the central route is that it flows by gravity. The water starts at a higher elevation and flows downhill all the way to Beijing. No pumping required for the main canal, but that meant the canal had to be built with an incredibly precise gradient, dropping just 0.0001. That's 1/10,000th in slope. Get that wrong. And water either flows too fast, causing erosion, or too slow, causing sediment buildup. The canal also had to cross rivers, roads, and railways. In many places, they built aqueducts channels that carry water above ground level, spanning valleys and crossing highways. In other places, they built tunnels to pass under obstacles. The logistics of constructing over 1,400 kilometers of precisely graded canal, complete with crossings and control structures, is staggering. The central route became operational in 2014, and it's already delivering billions of cubic meters of water annually to northern China. Beijing now gets a significant portion of its water supply from this route, easing pressure on local groundwater. Then there's the western route. This one is still largely in the planning phase, and it's by far the most controversial and technically challenging. The western route would take water from the headwaters of the Yangtze River on the Tibetan plateau and divert it into the headwaters of the Yellow River. The catch? This region is at elevations of 3,000 to 4,000 meters above sea level. The terrain is remote, mountainous, and seismically active. Building infrastructure here means working in conditions that challenge human endurance. The route would require multiple large tunnels through mountain ranges, dams to create reservoirs, and infrastructure capable of operating in freezing temperatures and high-altitude conditions. Estimated costs for the western route run into tens of billions of dollars, and completion, if it happens, wouldn't be until the 2030s or beyond. Critics of the western route point out the environmental impact. The Yangtze's headwaters are crucial to ecosystems throughout the river basin. Diverting water at the source could have cascading effects downstream. There are also concerns about impacts on the Tibetan Plateau's fragile environment. The entire South-North Water Diversion Project has already cost over $80 billion, with the eastern and central routes operational and the western route still in planning. When complete, all three routes combined would transfer nearly 45 billion cubic meters of water annually. That's about the same as the annual flow of the entire Colorado River in the United States. The human impact of construction was enormous. Over 330,000 people were relocated to make way for reservoirs and canals. Ancient villages were flooded. Agricultural land was taken. The social disruption was significant, though the government provided compensation and resettlement housing. Environmentally, the impacts are complex. On one hand, the project eases pressure on northern groundwater aquifers, which were being depleted at unsustainable rates. On the other hand, diverting water from the Yangtze alters ecosystems along that river. Species adapted to certain water levels and flow rates now face changed conditions. There are also questions about water quality. Moving water through canals and pipelines risks contamination from agricultural runoff, industrial discharge, and urban pollution. The project includes extensive water treatment facilities, but maintaining water quality across thousands of kilometers is an ongoing challenge. Economically, the benefits are clear for northern China. Cities like Beijing no longer face the immediate prospect of running out of water. Agriculture in water-stressed provinces has more reliable irrigation. Industries that require significant water inputs can continue operating. But there's a cost beyond the construction budget. Water doesn't come free. Users pay for the water delivered by the project, and those costs are passed on to consumers and businesses. There are ongoing debates about pricing. Should water be subsidized to encourage economic development or priced at full cost to encourage conservation? These are complex policy questions with no easy answers. But the physical project is moving forward regardless. Tunnels are being drilled. Pipelines are being laid. Pumping stations are coming online. The South-North Water Diversion Project is expected to be fully operational, including the western route, by sometime in the 2040s. When complete, it will have reshaped China's water geography, moving water on a scale that's never been attempted before. It's a testament to what modern engineering can achieve, and a reminder that solving resource scarcity problems at a national scale requires thinking big, really big. From railways climbing to the roof of the world, to dams that generate more power than entire countries consume, to tunnels that move rivers across provinces, China's infrastructure megaprojects are redefining what's possible in the 21st century. What do you think? Are these projects impressive feats of engineering, or does the cost outweigh the gains? Let us know in the comments below. Keep following Signum, where we bring you the most inane stories of the world's greatest megaprojects.